Much. Well, hi there. My name's Dean Kelly, and I got started into astronomy back, well, actually, when I was a kid, because I grew up out on a farm in Oregon and had all sorts of stars to look at. There's beautiful clear skies there. But it wasn't until 1996 that I officially got into astronomy, got my own telescope. That was after going to John Dobson star party and getting a chance to look through his scopes. And yeah, that was amazing and just convinced me that one day I needed to have one myself. Well, what we're going to talk about tonight is supernovas. So, how many people here have seen a supernova or even heard about it? I know that we're going to have people watching on YouTube that maybe can't raise a hand or anything, but we're going to talk about just exactly what they are, and then also, are they dangerous to life on Earth? And what would the universe be like? How would it be different if supernovas never occurred? Oh, we're going to explore these and other questions in this presentation. So 100 years ago, we believed that we lived in a quiet, safe universe. Without telescopes placed above Earth's protecting atmosphere, we had little evidence of cosmic radiation. But since the era of space telescopes, we now know the universe is filled with powerful radiation. Oops, I clicked the wrong thing there. There we go. We got gamma rays and X-rays. We got fast-moving particles that we call cosmic rays. This radiation is not the kind of radiation we can detect with our eyes. So where does it come from? Well, one source is black holes at the center of galaxies. Another is the powerful magnetic field that surrounds neutron stars. More commonly, however, the radiation originates from supernovas, the powerful explosion marking the end of a massive star's life. So, one type of supernova, the one we're mostly discussing tonight, is the explosion caused when a massive star dies and collapses. Now, only stars that contain 8 to 10 or more times the mass of our sun are going to go supernova. But during the explosion, the star is going to blow off most of its mass. And the remaining core will form either a neutron star or a black hole. So, where does this radiation come from? Well, stars are powered by fusing lighter elements into heavier elements in the cores of the stars. So, energy is released from fusion reactions and material at extremely high temperatures in the form of gamma rays, atomic particles like atomic nuclei that are blasted away at high speeds from the shock wave of the supernova explosion, and X-rays. And they're generated once the shock wave from the supernova explosion slams into the blown off layers of the star. So, what kind of stars are going to go supernova? Well, let's start this off by talking about something that we're maybe a little more familiar with, and that's the life of a butterfly. So, butterfly's life cycle starts as eggs, and then it becomes a caterpillar, and then a pupa, and then a full-grown butterfly. Grown butterfly lays eggs, and soon new butterflies are born. So a butterfly's appearance changes at each stage of life, changes that cause it to look nothing like what it did before. So stars also go through stages in their lives, stages that cause the star to change its appearance as it progresses through each stage in its life cycle. And stars of different masses progress at different rates and have quite different fates. So let's walk through the life of a star like our sun, and then the life of a hot, massive star. Stars of all sizes can be born as protostars from a cloud of gas and dust in our galaxy. So this is a star-forming nebula that we're looking at right now. And when the protostar compresses under the force of gravity and its core becomes hot enough, the star begins fusing hydrogen in its core. Now, for a sun-like star like ours, it's going to be billions of years that the sun remains pretty much the way that it is. It's going to be stable. It's going to be fusing hydrogen in its core. But eventually, after several billion years, it uses up the hydrogen in its core and turns into a red giant. At this point, the star goes through an unsettled stage where it starts losing its outer atmosphere in what's called a planetary nebula, which forms around the star. Now, planetary nebulas are not planets. This is just a name that was given to them a long time ago when telescopes weren't very good, and they looked a little bit like planets in a poor telescope. So that's how they got the odd name. Anyway, the cycle that's shown here continues on from the planetary nebula back into the cloud of gas and dust. And this represents the recycling of the elements created in the star. They're recycled back into the interstellar medium, back into gas and dust out there between the stars and the galaxy to provide material to make new stars. What happens to the core? Well, what's left over of the star, like our sun, becomes a white dwarf. The remaining core cools down and shrinks. And then after tens to hundreds of billions of years, the white dwarf cools off so much that it no longer glows and becomes cold and dark, and what they call the black dwarf. Now, strange to think that although our universe is 13 to 14 billion years old, there are no black dwarfs yet. There just hasn't been time for that. So let's look at the stages of life in a massive star. Now, you'd think that the biggest stars are the oldest ones. That's kind of how things work in general. Adults are bigger than kids. Big squirrel is bigger than baby squirrel. Doesn't work that way with stars. Unlike our sun, that's several billion years old, your giant stars, ones that are more than 8 to 10 times the mass of our sun, are only stable for a few million years. That seems like a long time, but trust me, out in space, that is no time at all. But during this time, it's busy fusing hydrogen in its core. So eventually it turns into a red supergiant. And after several million years, the star uses up all of the hydrogen in its core and becomes this way, this big red supergiant. The star continues to fuse atoms in its core into heavier and heavier elements until the core starts filling up with iron. And because the fusion process stops at iron, the core collapses under its own weight. It's no longer able to hold itself up by the heat generated during fusion. And when it does that, let's see, did we get there? There we go. That's when we get into supernova. And that's an explosive shock wave. And the energy generated from the core collapse starts moving out, heating and surrounding layers of the star, and kaboom! Most of the star is blasted into space in a supernova explosion. The cycle shown here continues on to form supernova back into the cloud of gas and dust. And this represents the recycling of the heavy elements created in the star. And during this supernova explosion back into the galaxy, it casts all of its materials to make new stars, new planets, and everything else that exists. So what becomes of what's left of the supernova? Well, anything that's left after that turns into either a neutron star or a black hole. If the remains of the star are more than 3 times the mass of the sun, that's when it turns into a black hole. So it's got to be pretty big. So only really massive stars explode as a supernova. So let's travel into the core of a red supergiant. Let's see if we get this little video working here. There we go. Okay, so we're diving in, going through the outer atmosphere of the star, and we're getting closer and closer to the core. Just there it is. There it is. This is where the star continues to fuse atoms into heavier and heavier elements until the core starts filling up with iron. And then the fusion stops at iron and the core collapses under its own weight, and then boom, an explosive shock wave, and the energy generated from the core collapses, moves rapidly outward, and most of the star is blasted into space in a supernova explosion, along with large amounts of high energy radiation. Now, my amazing 6-year-old granddaughter drew this picture recently. She's getting into astronomy at 6 years old, loves those books. And she had one that talked about supernovas and such. And so she drew a picture of what a star looks like when it explodes. Now, I was pretty impressed. I told her that actually it kind of reminded me of the Crab Nebula, pictures of that, good old M1, Messier 1. I also told her that I was going to be sure to use her drawing in the presentation. So anyway, let's look at some special effects of some stellar explosions. So gamma ray burst, or a GRB. What that is a short burst of a very high energy radiation from space. It may be less than a second, may last for several minutes. Now, one source of GRBs is the explosion of a very massive star, where most of the gamma ray energy released in the explosion is focused in narrow beams, and one of the beams just happens to be pointed in the direction of the Earth. So all this radiation coming at us from space might seem dangerous, and if we're too close to it, it is dangerous. So how close would a supernova or the source of a gamma ray burst have to be in order to damage life on Earth? Well, here on Earth, we know that radioactive sources like uranium, others, they emit gamma rays. If we get too close for too long, the exposure to the radiation is going to cause us harm. So how far away do we need to be? Well, does this look like home? It should. This is the Milky Way, or at least it's an artist's idea of the Milky Way. We can't really get out there and get a picture of it like this. So what we're going to do is we're going to zoom in a little closer. You can see where our solar system is down there. We're going to zoom in. We're going to find out how close we need to be for a supernova explosion to have problems here on Earth. I'm going to zoom in just a little bit closer. Okay, there we are. Now we've zoomed in far enough. So a supernova would have to occur within 30 light years of us for the radiation to affect life. That 30 light year distance is represented by the little white circle around the location of our solar system. The nearest star likely to go supernova is over 250 light years away. So we're safe for now, sure, yeah, no problem. Now, we found out that gamma ray bursts are more powerful than supernova. though. So let's zoom out again and see how close a gamma ray burst source would have to be to harm us. So here's the danger zone for the source of a gamma ray burst. It's going to have to occur within 8,000 light years. Then that's far outside of our galaxy. Our galaxy is about 100,000 light years across, and the nearest detected source of a GRB so far is over 1 billion light years away. That's a long, long ways, way outside of our galaxy. So, as far as we know, we're not in danger of any GRBs, gamma ray bursts yet either. So, in any case, there's still some amounts of radiation coming from space all the time. So, how has life on Earth been protected from this constant barrage of cosmic radiation? Now, strange as it may seem, Earth's atmosphere and magnetic field shield us from most of the high energy radiation. The atoms in our atmosphere absorb gamma ray and X-ray radiation, protecting us from that kind of radiation. Earth's magnetic field also deflects or captures a lot of the fast-moving atomic particles. But this also prevents us from detecting this radiation here on Earth's surface. So how does NASA study this kind of radiation? Well, there's a number of telescopes out there in space above the atmosphere to detect and study this radiation. So here's some of them. There's XMM Newton. It was a joint mission with Europe. It was launched in 1999, and Suzaku launched in 2005. It was terminated in 2015, though. It was a joint mission with Japan, and both of those studied X-ray radiation. SWIFT was launched in 2004, and GLAST launched in 2008, although we've since changed the name of it to Fermi. They're primarily gamma ray missions. Now, supernovas may seem dangerous, but if stars didn't die in the supernova explosions, if they just cooled off and collapsed, then the universe would be a very different place from what it is right now. The supernova explosion releases a lot of the elements created in the star during its lifetime, and also generates new, heavier elements, all in the matter of a few seconds, like the oxygen in the air that we breathe and in the water that we drink. How about silicon? It's in all of our electronics. Hey, you wouldn't be seeing this presentation if it wasn't for supernovas. And iron, we use it for steel. It's in our blood cells. We use it to build things. It's in the earth itself. Now, supernovas may seem dangerous, but a universe without supernovas would be a universe without life. So here's Orion. I'm sure that some of you are pretty familiar with it. It has stars that can go supernova, but which ones will eventually go supernova? It may look like a lot of stars are going to go supernova, but we can only see the biggest and brightest of all the stars out there. Over 85% of the stars in our galaxy are small stars like the sun, or even smaller than that. But the stars are so far away that we can only see the brightest ones without a telescope. And the brightest stars also tend to be the most massive stars, the ones much more massive than our sun. And it's the most massive stars that are going to go supernova. Well, I think that we can all appreciate how important supernovas are to the universe and even personally to us. Something that I've always wondered about, though, is what about all the other elements? The heavy ones out there, where did they come from? Well, supernovas created the elements necessary for life, but there's a lot of other elements that we're also very grateful for. Where did they come from? Supernovas can only create the ones that go up to 40 protons, like zirconium. But that's the end of the line there. And there's so much more after that. Where'd that come from? Well, back when I was doing planetarium shows, I would sometimes talk about how everything that exists came from exploding stars. Then I'd tell the audience to look at the gold ring on their finger. That used to be part of a star. Now look at the person next to you. They also, just like the prospector here, are made out of star stuff. Well, it turns out I was mostly right. But gold and most of the other heavy elements were created in the collision of binary neutron stars, the leftovers from supernovas. Now, neutron stars are compact remains of a supernova that just wasn't quite large enough to create a black hole. But they're no lightweight by any means. A teaspoonful of neutron star stuff would weigh 10 million tons. That's pretty darn heavy. So back in August of 2017, LIGO detected a gravitational wave from a galaxy 130 million light years away, NGC 4993. This cosmic disturbance came from a pair of city-sized neutron stars colliding at 1/3 the speed of light. I have a little video that I'm going to flip over to here. And this is a simulation of those neutron stars as they spin around, and they're going pretty darn fast. And you can see how they're disturbing the waves of gravity. And then wham, they finally explode and send off rays and the gamma rays and stuff. And this is where we get our GRBs, our gamma ray burst from. But we get a lot more than that. Let me get back to the presentation here. So once this happened, observatories all around the world were alerted about it, and they trained their telescopes on the area that the gravitational waves had come from. And for the first time, they were able to see the visual effects of the aftermath. And it's what's called a kilonova. A tremendous explosion to cause all of this, or collision. Over the next few days, they watched it fade away, and by observing the spectroscopic lines of this event, we were able to witness the alchemy of the creation of gold, as well as many of the other heavy elements. Now, this has changed some of our understanding about how the universe's elements came to be. Oh. Well, I forgot to mention about this, but this actually shows you the elements out there. And here you can see gold. Gold is clear down there with 79 protons in it, whereas zirconium is back up here at 40. So now you can see where the different elements come from. Now, I want to talk about one other thing that we experienced this last year, and that was the great dimming of Betelgeuse. Betelgeuse, 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 I've heard it pronounced several different ways, but it's the nearest star to us that has the potential to soon go supernova. Now, we don't know for sure how big Betelgeuse is, but mass-wise, they say that it's somewhere between 15 and 20 times the mass of our sun. Because it's puffed up our super red into a super red giant stage, if you were to replace our sun with Betelgeuse, it would fill most of the space out to about the orbit of Jupiter. Now, some of these figures have been changing just recently, and I'll get to those later. So in October of 2019, Betelgeuse began to dim. Now, this is in line with its normal variable star sequence, about 420 days. It dims, it brightens back up, dims, brightens back up. But this time it started to really dim. By Christmas of that year, it was the dimmest it had been in 100 years. Not only that, but it continued to dim right through February. So what was causing this dimming? Were we about to witness the first supernova in our galaxy since the year 1604? Think about that, over 400 years ago. Well, images of Betelgeuse from the Very Large Telescope in the Atacama Desert of northern Chile showed a dark shadow hiding some of the brightness of the massive star. Could this be Betelgeuse puffing off a gigantic cloud of material that, as it cooled, became a dust cloud? Or was it perhaps something else? Astronomers at the James Clerk Maxwell Telescope in Hawaii observed Betelgeuse in the sub-millimeter wavelengths of light. If this was indeed dust, then the star should actually be brighter at those wavelengths. The floating grains of dust should have absorbed and re-emitted the starlight, but they didn't. Infrared telescopes, like NASA's airborne SOFIA, should have picked up a glowing signature of dust if that was the case, but the signature wasn't there. So maybe it was caused by a giant sunspot, convection currents or such. Another theory is that this was the culmination of 3 different dimming cycles, all coming together at the same time. The 6-year cycle, the 420-day cycle, and the smaller 187-day cycle. Astronomers hope to use the Atacama Large Millimeter Sub-Millimeter Array, or ALMA, to observe Betelgeuse in infrared or sub-millimeter simultaneously, and hopefully solve the dust or not dust dilemma. ALMA is located in Chile and is the only observatory with that capability. However, COVID-19 pandemic came around and ALMA had to shut down in March of 2020. So they didn't get the chance to observe that. Now, one of the bonuses of further studies, however, is that we've discovered something more about Betelgeuse. It's actually in the early core helium burning phase, which is more than 100,000 years before it's going to go supernova. It's also smaller in mass and radius than we previously thought, somewhere between 16.5 and 19 solar masses. That's pretty close, but yeah, it's small enough that its radius would only extend, if you replaced our sun with Betelgeuse, would only extend about 2/3 of the way out to Jupiter. It's not going to cover Jupiter. It's about 750 times the radius of the sun. It's also closer. Up to most recently, we thought Betelgeuse was about 640 some odd light years away. Now it's about 530 light years from us, about 25% closer than we thought, but still safely distant. So analysis of this data is going to continue. And ultimately, if Betelgeuse did cough out a cloud of dust last year, it could teach us about the origins of life in the universe. If the dust camp is even partially right, Betelgeuse's dimming may have been the first time humans have watched the seeds of life being launched into the cosmos. So that's what I wanted to share about supernovas, and I hope that you found something out of there that's going to be enjoyable and useful, and that you know just a little bit more about it. Now, Tom, I'll give it back to you.